Okay. Hello everybody. Today we're going to start a new section in this course, which is online learning. And for those of you who are just joining in, there's a new link for a new whiteboard on the course website and also in the chat window here. So please use that, and we'll use that for this section of the course. Maybe for the next three or possibly a little bit of the fourth lecture. Okay. So here's a quick summary of what we've been doing so far, right? So we first started out by viewing learning, by casting learning as an optimization question. And then we moved on to three important optimization algorithms: gradient descent, accelerated gradient descent, and stochastic gradient descent. So we studied gradient descent in great depth, and that also allowed us to say some things about stochastic gradient descent and maybe gain a little bit of intuition for accelerated gradient descent. So let's think of this as our first algorithm, second algorithm, and third algorithm. So as I said at the beginning of the course, our idea here is to cover some of the important algorithms that are used widely within machine learning. So today, and in this next topic of this course, we are going to cover one more very important algorithm which shows up in all kinds of places, in all kinds of hidden forms, all over the place. Not exactly the form that we're going to state, but some things like that. So the idea today is to talk about online learning. We'll start with a very simple problem there, which is perceptron algorithm and what it tries to solve. And then we'll move on to the more general goal of online learning, which is called regret minimization. So what is online learning? So in a few words, what online learning is, it is the following. So you're trying to do some prediction or make some classification or things like that, but you have to do this on the fly. So in other words, you don't see all of the data at once. You need to learn, classify, predict on the fly. Okay? So in the way we've been looking at learning, we said, okay, you have the entire data set in front of you, and then you're trying to learn something for future examples. But here, there is no past and present. It's basically like you're always learning and you have to make the prediction immediately. Can you think of some examples where this might show up? Some example scenarios where this aspect that you have to predict on the fly and then learn on the fly is critical.
Maybe something to do with stock prices, like predicting a portfolio.
Yeah, right. Stock predictions. Right. So somehow, if you're trading using some machine learning algorithm, you don't have the data set forever, right? You have to kind of predict, then you learn something about how your algorithm is doing, some other feedback, and then you go and predict the next day and so on. Right? You have to constantly revise your algorithm, update your algorithm, so that you can predict, the next example better. Any other things that you might think of?
Like things to do with like tweets. I don't know.
So let me say a bit more, a different form of that, which is advertising.
Yeah.
Right? So especially online advertising. Or what Harry was saying is basically like, recommendations. So you're shown, you see an ad, let's say you're searching for something on Google, you see an ad, you click or you don't click. So when you don't click, it's like an input and then you have to show a new ad. So the algorithm behind the web page is trying to kind of revise its model for you and come up with a new prediction. Right? It's always predicting on the fly. Any other examples? The classical example for motivating this was weather prediction. It's going to rain today, not rain today, and then tomorrow you have to make the same prediction again, and so on and so forth. So there are two aspects to online learning. One is that while you're aggregating data, in this phase also you have to make predictions. I think that's the main difference from just batch learning or something like that. There is a phase where you can just collect data and then you have to make future predictions. But here, even in the collecting phase, there is some cost with making bad predictions. Okay? And if you think of any other examples, there are lots. In real life, everything we do is online, I'd say. Right? Think of, let's say you're playing a game of poker. You can't say I'm just going to sit out, keep losing, or do something for the first 100 games and then come up with a magical best learning algorithm, right? You have to be good even in the phase where you're trying to figure out what the opponent's strategies are. Right? So in all of these cases, there's this challenge or important aspect of trying to make predictions on the fly without enough data. Okay? So if this is our, this is the application or domain that we're trying to handle, we had to first come up again with some mathematical way or computational model for the problem that we're trying to solve, right? For learning, which was, kind of subtle to begin with, but we were pretty successful by changing it into this optimization framework, right? So we said, okay, let's try and do ERM. And we were already seeing some successes for that using GD, NAGD, and SGD, and so on. And many applications use that. But what would be a good computational model, mathematical model for online learning? So how to formalize online learning? Okay. Any suggestions?
You could do like a batch, but always include the new sample.
So, but then how are you going to judge whether one algorithm is better than the other? Like, are you trying to say maybe we can use ERM, but do a batch where you include the new sample?
Yeah, I was thinking you would do like a separate training evaluation and test evaluation.
Okay, so idea one, let's say separate training and test, and somehow the test part is like the on the fly part phase you're thinking, right?
Yeah.
Okay, so that sort of makes sense, except that one thing we have to keep in mind is that in the framework of ERM and so on, we have to collect a lot of data for it to be applicable to begin with, right? So in the training phase, if you have no guarantees, you might be incurring too much loss in this training phase, which might be prohibitive for your online learning application. Like let's say stock market, let's say you can't do simulations and you have to really deploy money in the market. You can't be in a training phase for the first 100 days where you just keep on investing money, right? So there are applications where what you said would work. In fact, for things like advertising and so on, that makes a lot of sense. And that's what many online advertising firms do. There is like a training phase, which kind of runs every now and then. And then for each person, you customize it a little based on their evaluations for the day. Okay, but let's try and go for something even more general. And it is actually a non-trivial thing to phrase it in a very, very abstract and generic way. So there are two ways that people have looked at. And So one is something called, it's a very stringent model. It's called mistake bounded model. I'll tell you what that is. And the third one is the regret minimization framework. So the third model is really important in statistic and in modern machine learning applications. Even though it's kind of motivated by the study of online learning and things like that, it has applications even for the usual batch learning setting where you do have the entire data set in your hand. But sometimes online learning algorithms have better performance even in those cases. I'll try to, maybe say a few words about why that might happen and when that might happen later on. Okay, so today my goal is to talk about this more stringent measure called mistake bounded model, and we'll see what we can do about it there. So what is the mistake bounded model? And all of these are connected, mistake bounded model is connected to pack learning, it's regret learning minimization is connected to pack learning and things like that. So at a high level, what mistake bounded model is asking for is the following. You're seeing these predictions I have to think of weather prediction, right, or stock market prediction. And I'm not interested in the exact numbers. At the first level, I'm only interested in a single bit of information. You have to tell me whether the stock market is going to go up today or down today. Right? Each day I ask you in the morning, is it going to go up or down? And then I'm going to count how many mistakes you made over your entire prediction period. Okay? Does that make sense? So number of mistakes made by prediction algorithm. Okay. So you have day one, you see x1, which is kind of your input for that day, and you make a prediction. So let's say y hat 1 is your prediction, and then you get to know the true label. Okay, so this is what you see, and then after this you get a cost, right? So let's say if your prediction is not equal to the true label, and here for simplicity let's consider the case where the true label is just binary. Think of a classification example, right? Is the stock market going up or down? Right, that's it. So now you're doing this every day. That's the game that you're playing. Day 2, the same thing again. And you have to count total number of mistakes made. Okay. So if I ask you to make just a bounded number of mistakes, I give you a budget of 100 mistakes, and you can only make 100 mistakes in the course of your entire life, right? It's a very, very stringent requirement, but nevertheless, some cases you can actually design algorithms like this. And it might seem like a very stringent, sort of useless restriction, but as you will see, thinking about the problem this way leads us to an important algorithm which has many other applications. And it will also give us intuition on how to sort of refine this framework further to make the model less restrictive. Okay? So, just as before, let's suppose that the labels are coming, the true labels. Are generated by H from some hypothesis class. Right? So, like in packed learning, we had an underlying hypothesis class which was generating the labels. And here also we can, to start with, assume that let me put a star. The true label is some hi star xi. This we don't know. We don't know what h star is, right? So there's some true underlying thing which is generating the label. We don't know what it is, and I'm trying to figure out h star, which is kind of the same learning problem as before. But now the requirement on me is that I make a bounded number of mistakes in the entire run of the algorithm. Okay? Does the question make sense?
Are we still assuming, because I know for our original problem, we were assuming that X just came almost like IID from an underlying distribution. For a lot of these applications, aren't X's going to be correlated over time?
Right. So that's the cool thing about mistake bounded model. Somehow, if you think of mistake bounded model, you don't have to think about the underlying distribution anymore. It kind of saying, so there is some conversion which says that, if there is an algorithm in a mistake bounded model, then there is a packed learning algorithm for the model with a similar sample complexity. But when you think of the mistake bounded model, it makes sense to ask this question even without assuming there's an underlying distribution for X. Because somehow you say that, if my distribution is kind of all over the place, I make certain number of mistakes, but after that, I know exactly what H star is. And then I don't make any more mistakes. Okay? And let's see an example. I mean, again, it seems kind of, way too hard to satisfy, right? Imagine I told you that in your entire 4 years or, 2 years of study at UCLA, you're only allowed to lose 10 points. Maybe we should try that model one day. But let's see if you can do anything meaningful under such a strong learning requirement. So the example that I'm going to talk about today is online learning of half spaces. Okay, so half spaces, are one of my favorite classes for two reasons. One, they're very good for teaching important learning algorithms and important learning principles. And also, historically, they have been very important for coming up with many state-of-the-art learning, applied learning algorithms, like support vector machines and perceptron algorithm and variants of it, and things like that. So, what is a half space? This is something that we already saw before. So the domain is just d-dimensional vectors, and the label space is, let's say, 1 minus 1, and the hypothesis class is just the sign. Okay, so geometrically, you just have okay, no, the drawing software is not that good, but let me do this way. So geometrically, you have a hyperplane in d dimensions, and all points on one side would be labeled positive, and all points on the other side are labeled negative. Okay, so this is my W star, right? And so, like, the perpendicular is W star, really. Let me make that clear. Okay, and so along with the half space, we'll show that we can learn half spaces in the online setting in a mistake bounded model under one important assumption. Okay, so what I mean by the online learning of half spaces, I'm trying to learn what this W star is, but I have to make a prediction for each example as soon as I see it. On day one, I give you x1, you have to make a prediction, and after you make the prediction, I show you what the label is, what the sign of W star comma x is. On day two, the same thing, and so on and so forth. And I want to do online learning of half spaces in the mistake bounded model, meaning in the entire course of the algorithm, you cannot make more than 10 or 20 mistakes, something like that. It's a bounded number of mistakes. By bounded, what we really mean is, if I run this algorithm, like this process, an infinite number of times, the number of mistakes is bounded. I'm not particularly interested at this point on what the bound is, but it does not go to infinity if I keep running this process every day forever. Okay? And in fact, I mean, we'll actually come up with a very precise quantitative bound, so that's okay. All right. So, and thinking of this online learning problem led people to come up with this very important notion of when a half space is much easier to learn than other half spaces. And this is a very important notion, shows up all over the place, and it's called margin of a half space. Right? So what I'm going to do for this lecture, and something that I've done before also, is that you notice that here there is no threshold for activation, right? I made the half space kind of zero centered. It's going through the origin, right? So usually if you think of like any majority or some kind of threshold, you'd say, okay, maybe if the sum of the x's is more than 10, I'd say 1, otherwise I'd say minus 1, right? You would like to have a threshold. But for simplicity, let's assume that it's actually going to the origin. When it is not going through the origin, you can just make some shift in x and get the general case with the affine linear function also in this framework. But I'm going to only focus on half spaces which go through the origin. All right? Make sense? All right. And then the notion of margin is the following. This is a very restricted. Okay. All right. I thought I could draw any rectangle, but seems like I can't. So basically margin, if I tell you that there is a half space which classifies the examples correctly with with good margin, means that there is no point in your dataset which is close to the boundary of the half space. Right, so some of things which are very close to the boundary are harder to classify, right? You know, if you think of any election, if there's exactly 51 versus 50, that's kind of harder in some sense to find the truth of than when it's like 60-40 or 70-30, right? And margin is kind of a quantitative way of formalizing that. So what's a good measure to say that there is no point which is close to the boundary of the hyperplane in d dimensions? What would be a good mathematical way of saying that?
Like the absolute value of the inner product is at least.
Exactly. Right. I would like to do that, but maybe you have to scale the example a little bit, right? Like, you know, the absolute value of the inner product is the right measure, but it's helpful to scale. I mean, you need to scale the examples a little bit for that to make sense. Okay. So the right notion of margin is basically what you said. It's the min over okay, we just scaled the absolute value of the inner product by the norms of the individual vectors. Okay. So it measures how far, like, you know, what's the kind of wiggle room that we expect. So things in this region are hard for us, or we expect them to be hard, right? Because they're so close to the boundary that, you know, maybe they're hard to classify. And conversely, if we expect that there is no point close to the boundary, that might be an easier learning problem to solve. And if you have ever seen support vector machines, this notion of margin also comes up very importantly there. And we'll use the letter gamma to denote the margin of the half space. Does the setup make sense? So now we are going to do the following. Design an online learning algorithm, right? Or actually, you know, let me write it. Learn half spaces with margin with bounded number of mistakes. Okay? Okay, so that's our goal. I'm giving you examples xi comma yi, where yi is sine of w star comma xi, right? And we know that the half space has a margin on your entire distribution. We don't know what it is, we just have a margin. And our goal is to come up with an online learning algorithm. I have to make predictions on the fly, but I can't make too many mistakes. Okay, so when we come back, let's take a 5-minute break, and when we come back, we'll try and answer this question. And along the way, again, as I said, this is a lead up to an algorithm as opposed to a problem. So the lead up will be to, this is all the motivation for studying the perceptron algorithm, which will then allow us to go to regret minimization. Okay, so let's take a 5-minute break, and when we come back at 10:35, we'll come up with a very simple algorithm for this problem. Let me pause the recording. Get started. So to start with, let's color is bad. Let's assume, actually no assumption, but we can just say assume that the norm of W star is 1 and the norm of the examples is also 1. So I'm going to normalize all W star and X to have norm 1. And in this case, the margin just becomes, what was suggested earlier, which is the minimum absolute value of the inner product between W star and X. Okay. Since it's anyway, the margin is kind of the ratio, I'm just kind of normalizing my examples to have norm 1 so that I don't have to carry these things around. And so here, the black line here is the W star. And, we have to make a prediction each day, right? So initially, here's how my algorithm is going to proceed. Initially, I don't know anything, right? So W0 is some random vector. I start with a random vector, which I'm denoting with this red line here. Okay? It's a random unit norm vector. And so what does it mean? My classifier would say that everything to the right of this red line is a positive example, and everything to the left is a positive example, is a negative example, right? But the truth is that everything above this black line is positive, and everything below the black line is negative, right? So what do you do on day 1? So on day 1, you get an example x1. And what do you predict your label? What is your prediction for that day? Say, okay, y1 hat, my prediction is sine of W0, comma, x1. Right, I don't have no idea to begin with. This is the first example, so I'm just making kind of a random prediction. Right, that's fine, you're just making a random prediction, but what's important is how you learn after you know the truth. So after this, you see y1, the true label. Now you have to learn from the truth. How do you learn from it? What should you do in this case? If you're correct by some chance, do you want to do something? What do you think? If correct, do you want to do something? What do people do if they're correct? Do they learn from their mistakes or from when they're right?
So you do nothing if you're correct.
Yeah, exactly. So you do nothing, just like all people. Why change something when it is working, right? If wrong, meaning you make a mistake. Again, there's a lot of hidden Zen philosophy here, is that you learn from your mistakes only. So what should you do here? If you make a mistake, that means you need to update your hypothesis, your W0 somehow. And what would be a good way to do it? So let's think of this diagram, right? So I saw x1 is some point on this circle because it's a unit norm example. And if I make a mistake, what does it tell me about x1? Where should it lie? I don't know what this W star is, but just, theoretically, just in terms of mental picture, where would it lie?
On the other side of.
Well, if it's on the other side, but if it's here, then it's not a mistake, right? Because both of them would be negative.
So like one of the sections that are like on one side of W star, on the other side of W0.
Exactly, right? So if I make a mistake, that means my x1 kind of lies in this region. In either one of these two things, I don't know. I mean, I really don't know what even W star is, so I can't really imagine where it is. So, for example, if my x1 was here, that would be a false negative. A false negative, meaning that I said that I gave out a label which is -1, but the true label is a +1, right? So this is false negative and this is false positive. Okay? So if I'm being somewhat silly and when I know that, let's say I make a false negative mistake. So here's my W0 and here's my x1. Maybe let me use the red line. Right, and this is my W star. Okay, so when I make a false negative mistake, meaning something I classified as negative but the actual label is positive, what do you see in the picture? What's a natural way to update W0 to make it somewhat closer to where W star is? What do you think? Any suggestions? So in the picture, there's something nice happening, right? You can see that when I make a false negative mistake, x1 tells me if I move towards x1, then I'm going towards W star. Right? Because x1 is something that W star labeled as positive, so it's on the positive side of W star, but I labeled as negative. Right? So intuitively, it makes sense that moving towards x1 would, maybe make me more pointed towards W star, which is my eventual goal anyway, right? I want a vector which is kind of aligned with W star, because in that case, I would get all labels correctly. So what would be a natural way to do that? So what should I update my vector as?
Would it be W0 plus x1?
Exactly, right? Just move towards it. We don't know what it's going to do, but it's a simple rule to at least get the right direction. And how about the other case? And you can see from the picture here that in the other case, if I move towards x1, then I'm moving away from W star. So what should I do? Right? This is where x1 is, this is W star. So if I add these two vectors, I'm kind of going away. But instead I want to go towards W star. So what should I do in that case? Well, you know,
Subtract x1.
exactly, that's it. That's a natural enough algorithm. You know, if you, my true label is, if I make a false negative mistake, I try to correct it sort of in a very heuristic way by just adding my x1 to my current state. And if I make a false positive mistake, then I just subtract it. Right, so that's it. So that's our algorithm, and let's write it more formally. And this algorithm is called the perceptron, or was called the perceptron. It's a very old and historically important algorithm. It came out, I think, in 1954 by Rosenblatt. It's kind of, you know, funny to read the history behind this, but I'll say a few words about that. So basically, here's the algorithm, right? You know, W0 is a random vector, and on day I, Wi is Wi minus 1. Let me write it as a case analysis, right? No mistake. If I don't make a mistake, I just keep it as it is. If I make a false positive mistake, actually it's easy to just write it this way. Okay, that's it. This is the famous perceptron algorithm. Usually Rosenblatt. It's a very simple algorithm, right? Okay?
Oh, wait. For the mistake, shouldn't that be Wi minus 1, though? Like, for...
Oh, yeah, sorry. Yeah.
Yeah.
I don't know what that should have done, but yeah. Okay? Alright, so let me just, show you something funny about what this... So this algorithm came out in 1954, and, or like, maybe I got the year wrong, it was 1958 actually, but... so at the time, they really thought that this algorithm would solve all pattern recognition problems, because half spaces, I don't know why they thought that, but just let me show you something very funny. Okay, this is an article from like New York Times in 1958. You can see a new Navy device learns by doing. That's basically like online learning, right? And psychologist shows embryo of computer designed to read and grow wiser, because it's refining its model continuously, and the algorithm is basically the perceptron algorithm. It was running on this $2 million 704 computer. $2 million in 1958, you can imagine that's a huge deal, right? It became kind of a big deal. Popular press picked up, all kinds of news outlets picked up. I think there are some specials also on it. But then it also led to a backlash, right? Because we know that we can see immediately that it's not really as remarkable as this popular press article makes it. And even if you were alive in 1958, we would have known that, right? And hold on, let me go back. Where is that? It's a very funny history. So basically, there was this huge hype around this algorithm. And there was a lot of flux towards like, perceptron, iterative layers of perceptron. If you think about it, if I compose perceptrons on itself, that's just a deep neural network, where the activation function is just the threshold function. Right, so people started looking at that. So perceptron was kind of the beginning of the study of neural networks back in 1958. But there was so much hype around it. But then there was this other result due to Minsky and Papert. Wait, where did it go? Can you see the Frank Rosenblatt, this snippet, the purple one? Yeah, you can see it. Okay. So basically, this is a snippet from the textbook of Bishop on pattern recognition, where, so what happened was essentially like, this perceptron algorithm came, it became a huge kind of, he implemented it as a parallel hardware. You can imagine, that sounds great. Again, but this is remarkable, right? This is 1958. But then theorists were like, okay, this is not going to solve all learning problems. And there was this paper by Minsky and Papert, in fact, published in a book form back in the day. It's called Perceptron, and it showed that there are simple functions which are not half spaces, really, right? You cannot compute everything by a half space, even if you expand the feature space in some way. So they showed that, and this led to what is known as the first AI winter, because the funding for neural networks completely died after this book. And then there was a second revival, and then a second winter, and then a third revival, and I think we are in third or fourth summer of neural networks now. And maybe this is here to stay. Yeah, it's kind of a funny historical detour, but let's go back to substance. So now we have the okay, this is a simple algorithm, but what does it do? What can it achieve? And we'll show that, as simple as this algorithm is, it is indeed remarkable in that you can say the following about it. Remember, we are learning in the case where there is a margin for the half space, right? So perceptron makes at most these many mistakes. So it is indeed a very good algorithm for learning half spaces in an online fashion even. Right, it is an online algorithm. You're making a prediction as soon as you see an example. You don't have to wait for all the examples to accumulate. And if you think of margin as being some small constant like 0.1, right? Then it's saying irrespective of what dimension space you are in, you might be in a million dimensions, my algorithm is only going to make at most 1 over gamma squared plus 1 mistakes. So the margin was 0.1, meaning things are not that close to the boundary. Then the number of mistakes is bounded by 101. Okay? So that's kind of a pretty nice guarantee. So recall gamma is the margin. Okay? Does this statement make sense? Alright, so let's prove this claim, right? It's a very simple algorithm, and the analysis is also simple, and the analysis comes from 2 steps. So the first is something about what this algorithm is doing for each mistake, right? So if there was a mistake on day I want to say that W star comma Wi. So the punchline of the analysis is that each mistake tells you, or you can show that for each mistake, you learn something about W star. And by learn something about W star, I mean that you move towards W star. And what's a nice way to quantify you are moving towards W star? What would be a nice way?
The inner product is
Exactly, like the
normalized
inner product
is approaching 1.
Yeah, I mean, you want to say 1, but there's a small caveat. For now, let's say it's increasing, right? Somehow you're getting more and more correlated with W star. So in fact, you can show the following, which is each mistake increases your inner product by an additive gamma. Okay? And so why is that? Well, let's just check what happens, right? So when we make a mistake, what's the thing that we do? We do Wi is Wi minus 1 plus Yi times Xi. Okay? Right, so let's just take the inner product. All right, now what can you tell me about this term? Yi times W star comma Xi. What can you tell me about it?
The sign equals yi.
Exactly, the sign equals Yi. So what is this number really? It's always going to be positive, right? Because if the sign of W star comma Xi is negative, then Yi is negative. So it kind of annuls the sign and you get 1. Right? So this is actually equal to plus the absolute value of the 2. Of the inner product, which we know is at least what? By our margin assumption, this is at least gamma. Right? The margin assumption, as we said, gives us a lower bound on the inner product of W star. So somehow, as long as your example is not very close to the boundary, you gain something in terms of how much you move towards Wi. Right? Okay, this sounds great, but are we done now? I'm saying that the angle is kind of not the angle, but the inner product is always increasing. Is that good enough? And am I done now?
No.
Why not?
Is it because you can overshoot or something? Or
Well, I mean, I'm increasing the angle, but I'm also increasing the norm of Wi, right? I'm adding vectors each time, right? I mean, I can increase the inner product by just doubling my vector trivial, or just scaling it up. That increases the inner product by 2 times. But that's not really helpful, right? Because, it just scaled things.
Don't we want the normalized inner product to be?
Right, so that's exactly what we want. We somehow want to say something about the angle and not just a numerical inner product. So to control the angle, we have to somehow say something about how much the norm of Wi is increasing. So somehow we are saying something about, okay, the inner product is increasing by so much. And what we complement that by saying that the norm of the vector is not increasing at the same rate. So here's the second claim, which is that it's not a star, this is the square, is at most I mean, when we don't make a mistake, it's actually the same. And when we make a mistake, I'm saying the norm squared increases only a little bit. Okay. And why is that? You know, the proof is really by a picture. So let's say I'm here. This is my wi minus 1. And you know, wi minus 1 might be a vector which has much bigger norm, right? Here's my circle. Okay. And you know, maybe let's say I made a false positive mistake. Oh, sorry, yeah. So in that case, this is my xi. So I add my xi, and this is what wi is. Okay. So we know that this is exactly wi minus 1 plus yi times xi squared, right? You know, that's the definition. And what do we do when we face such a thing? We just expand it out. Well, the punchline here is that if you go back to this picture, right? And basically when you make a mistake, okay, this is W0. So when you made a mistake here, what can you tell me about the angle between x1 and W0 here? When I made a mistake with which is false negative, what's the angle between the two? From this picture, what does it look like?
Right angle?
It's more than a right angle, right? Like, you know, it's an obtuse angle, right? Because somehow you're on the negative side, right? So it's more than 90 degrees. So that kind of tells you that when I add something, the norm doesn't increase so much. Okay? So basically here, this angle is greater than 90 degrees. Well, let's just expand it out and see what happens, right? You know, I use my usual formula, and then I get 2 times the yi times the inner product. Okay? And what is this term? The norm of yi times xi squared? Well, we normalized each example to have norm exactly 1, and yi is just 1 or minus 1, so that's 1, and then I get this inner product. But remember, we made a mistake. So what does it mean we made a mistake? What can you tell me about yi and this sign of wi minus 1 comma xi? My prediction for that day, if I make a mistake, what does it mean?
They have different sign.
They have different sign, right?
So it's a negative.
It's negative. So basically, this sign is not equal to yi because we made a mistake. Right? So that means that this whole thing is at most this much. So the norm squared is kind of increasing only by 1 each time. Okay? Each time you make a mistake. I should say, okay, so this analysis, this statement was shown in 1958 and 1962 independently by several people. Bloch, Rockoff and others. I don't remember the names exactly, but you can look it up if you want. Okay, so now we have this very interesting two claims, right? So let's put them together. So the first one says that is greater than or equal to wi minus 1 comma w star plus gamma if mistake. And we also have that okay. So let mi be number of mistakes by day I. Alright, if that's the number of mistakes that I made up to and including day I, what can you tell me about the inner product of wi and w star? It's at least something, and what is that? Well, we know that it increased by mi times gamma, okay, and then it's plus this w0 comma w star. Right, you started out with something, and then you keep on increasing by at least the number of mistakes. And what can you tell me about the overall norm squared of wi in terms of the number of mistakes? What's a good upper bound on that? Any guesses? So, just apply this iteratively, and we get that the norm squared is at most 1 plus mi. Now, I initially started out with norm 1. Each mistake might increase my norm by 1. Right? And remember, this is actually a strong constraint. Like, if I have a long vector, and when I add something of unit norm, I might actually increase the norm much more than just a single unit norm. Like the Pythagorean theorem might not be tight, but here it is. Okay? Great. So what should we do now? I have this inequality on the inner product here, like a lower bound, and we know this is at least minus 1. Okay, and I have an upper bound on the norm. So what can I do now? Somehow it seems like I've ended up with apples and oranges here. I have a lower bound on the inner product and an upper bound on the norm squared of my wi. How can I mix these two bounds together?
So then you can upper bound the normalized inner product.
Right. So basically, the inner product is always at most the norms of the two vectors. Right. This is an inequality that it's called Cauchy-Schwarz. I mean, we also used it in the analysis of gradient descent. That the inner product of any two vectors is always at most the product of the norms of the two vectors. Right. And this is exactly square root of 1 plus mi, or at most. Okay? So what do we end up with? We end up with something sort of weird, right? It's saying mi times gamma minus 1 is at most square root of 1 plus mi. Okay? This is true at every time step, no matter what. Okay, and now you can see that this already tells you that mi cannot be too big. For example, if mi is bigger than some huge, let's say mi, the number of mistakes at some point was something like 2 over gamma squared. Then you get a contradiction because like 1 plus square root of 2 over gamma squared is something like square root 2 over gamma, but on the left hand side you have 2 over gamma. Right? It's like a quadratic equation. You can solve for the root, and basically this implies that mi times is at most 1 over gamma squared plus 1. Okay? I mean, this is equivalent to saying gamma squared times mi minus plus 1 minus mi is less than or equal to 0, I think. Well, anyway, let me not belabor this, but basically you can write down a quadratic curve, and saying that it's negative gives you an upper bound on mi. Okay? Does it make sense? Like for instance, if I tell you that x is less than or equal to square root of 1 plus x, right? This is only true if and only if x is less than or equal to, implies x is less than or equal to like 2, for example. Right? The same thing. Okay, so that's the proof of this classical result on the perceptron algorithm. And there's a very simple algorithm for learning half spaces, which is an important hypothesis class. Imagine your predictions are based on some kind of weighted majority of the features. And it's saying as long as there is margin with your classifier, there's a very simple algorithm which gets a very strong guarantee on convergence. That you won't make more than these many mistakes in the entire run of your algorithm. Okay? Any questions about this? There's a question, does this also mean if you make mi mistakes, we can say that wi is within some margin of w star? That's a good question actually. So, it's not clear, like somehow you get this angle and yeah, I think basically as you make more mistakes, it forces you more and more to align with w star. Alright? So, which is kind of counterintuitive, right? So, if I want to learn the actual w star, then I have to say more mistakes. Because if I keep seeing examples where I'm always right, I might just be stuck with the initial w0 itself. So, I'm not updating my prediction vector at all, but I'm not making any mistakes. Right? So if you think of this as a game where I'm the predictor and you are giving me examples to defeat me, you're giving me examples to make mistakes, or let's flip this side, you are the student, so I'm trying to give exam questions to defeat you or make you make many mistakes, right? But the point is that whenever I make you make a mistake, I reveal something about the truth and you correct yourself. Okay? And that's what's really playing out in this simple setup. And next, we're going to try and sort of generalize this and see what we can say about more general classes besides just half spaces. Now, the fact that we can learn this class with in the mistake bounded model is great. And there are few other interesting classes where we can indeed learn them in the mistake bounded model. But as I said at the beginning, it is a very restrictive class. And the only reason we are looking at it here is because it leads us to this very nice and simple algorithm, which is the perceptron algorithm. Okay? Now, before going to the more general formalization of online learning, which is kind of more broadly applicable, let me say a few words about how this perceptron algorithm connects to something that we saw in the last class and the class before. Can you think of any other algorithm which looks a little bit like the perceptron algorithm? We saw something like this in the last few classes. Well, this is a suggestion here, which is gradient descent. In gradient descent, you had to look at the entire set of examples, right? If you think of gradient descent with ERM, you had to look at the entire set of examples and then compute the gradient. Whereas in perceptron, which is a special, just kind of working in the online learning framework, you had to make a prediction based on a single example, right? So it's really SGD, okay? And that's one of the reasons why SGD is so useful. I mean, not one of the reasons, but it is, maybe not the most important one, but it is an important reason. Is that SGD is applicable even in the online learning framework. Okay? You can adapt it depending on the situation to online learning. So in particular, I can view perceptron as exactly SGD with some kind of hinge loss. Okay? So what do I mean? So what is SGD update? So if I have some recall, SGD update was somehow Wi was Wi minus 1 minus eta times G of Wi minus 1. Estimated for the gradient, okay? And we said that, in the context of ERM, SGD shows up really as, or one specific estimator for the gradient was to just pick a single example and evaluate the gradient there, right? So it was gradient with respect to W of L of HW of Xi, comma yi, right? Where Xi comma Yi was your random example from your dataset. Okay, you picked a random example and then use that to compute your gradient at that point and then update your parameter vector. Well, we were picking random, but if I were to use it in an online setting, I can, right? What would I do on each day? I would just do this exact same thing. I would make a prediction based on Wi, but that's kind of beside the point. The main thing is how do I update my prediction vector or my parameter space, and the way I would do it is to compute this something like this. Okay, does it make sense? Right, so we can deploy SGD for online learning problems. Okay, and it's not just a theoretical connection, which kind of it's an intellectual curiosity. But some of the very important practical hacks that people devise for making SGD work better for things like deep neural networks, especially something like AdaGrad, right? They are motivated by viewing SGD as an online learning algorithm, and there are better online learning algorithms, better ways to choose step sizes and things like that, and you bring them here. Okay, but let's go back to perceptron, right? So I want to say that perceptron is a special case of some update like this for a suitable loss function. Okay, so my parameter family is just linear predictors. Okay, But what should the loss family be? Something whose gradient actually tells you, gives you exactly the update that we had. What do you think the loss function should be? So, perceptron update. So the perceptron update was Wi minus 1 plus eta times yi xi if mistake. Okay, and the loss is going to be hinge loss. In particular, I'm going to say that L of a comma b is 0 if sine of a equals sine of b and is equal to a if sine of a is not equal to sine of a. Or actually, you know what, it should be a big positive number. So say minus a times okay, maybe let's write it this way. Okay. So if I think of the label as 1 minus 1, it's saying, you know, if my sign is correct, I made no mistake, then the loss is 0. Whereas, you know, if my sign is wrong, I penalize you more if you're very wrong numerical. It's not just the sign is wrong, but you know, the sign should have been positive, but you said you predicted minus 100, then I'm going to actually penalize you 100. Whereas if the sign was positive and you only predicted minus 1, then I'm only going to penalize you 1. Right, some kind of, you know, smooth penalty scheme. Okay. So does this make sense? So if I applied SGD update is going to be Wi is Wi minus 1 minus eta times gradient W of L of W comma xi comma yi. Right? And you can see immediately that what is this gradient? If I don't make a mistake, then it is 0, right? I mean, I shouldn't say gradient, but it's going to be subgradient. This is not a differentiable function. It's kind of, it looks like this, right? So as a function of a times b, this is what it looks like. Okay. So when a times b is positive, this is L of a comma b. When it's positive, I just get 0. When it's negative, I just get the value of the negative value. Okay. So if I don't make a mistake, then the gradient is 0. And when I make a mistake, what is the gradient?
Minus yi xi.
Exactly. So minus yi xi, so end up with exactly this. Right? So essentially, perceptron is SGD with hinge loss. And step size is 1. Right? Isn't this remarkable that someone in 1958 came up with an algorithm for completely different reasons, which looks like, you know, SGD applied to an important loss function. Okay. Does this make sense? I mean, we can't use the analysis of SGD directly. There is a way to make that work, but I think it's a bit more complicated than the simple, straightforward analysis of perceptron. Yeah, so the batch size is also one. So, you could potentially try and speed it up and things like that. And if you go back to this New York Times article where it says, it's very fast and it's parallelizable, I think it's mainly talking about the advantages of using SGD versus, something else. Okay. All right, so that's all I wanted to say about perceptron and how it connects to SGD. And we'll come back to this connection to online learning and like some kind of optimization questions, hopefully after, couple more lectures, that there is kind of a real back and forth between these two perspectives, where you can think of online learning as doing some kind of optimization, but in an online setting. Okay, so now let me, in the little bit of time that I have, let me talk about a more general framework of online learning. And this also is not the most generic, but I think to get to the most generic one, I want to go step by step. So we started out with a very simple setup where you're doing this online learning in a mistake bounded model. The slightly more general setup we'll see is what is known as online learning or a learning with experts. Okay. So if you think of the problem here is kind of in the online learning setup, but the mathematical model of everything is going to be different. So in particular, so let's say we are kind of playing this game where we are trying to predict in an interactive environment. Okay. And our only knowledge of the environment comes through some information that experts give us. So imagine you're trying to make stock predictions. You are trying to make your own investment, right? I have some money, I'm trying to invest in some stocks, and I don't actually get to see all the, or at least I don't want to dig into the whatever, quarterly reports of every company or do some other sort of whatever time series analysis and things like that. But at the same time, also not too lazy. So what I'll do is collect the predictions of various experts. The first expert is maybe Wall Street Bets. The second expert is, something like Motley Fool, and maybe all things like that. And then based on their predictions, I'm going to make my guess. That's it. Okay. I see some people crying when I said Wall Street Bets. I didn't see anyone laughing though. Okay, so learning with experts is exactly in this setup, right? So somehow your only interaction or information about the environment comes through predictions of experts. Again, it seems artificial, and it is somewhat artificial, but you should really think of it as an abstract framework which is very generic and allows us to cast many learning problems in this setup for various applications. That's a good question. Zoom only gives us positive reaction. Okay. All right. So now, so let me say it. So predict based on prediction of experts. So you should think of this as some kind of aggregation mechanism, right? I have predictions of various experts and I'm trying to aggregate the predictions into something which I think might be better. Right? So imagine you have various learning algorithms, like you have 1,000 models that you build, and you have to combine all of these into a better predictor or a single predictor that you want to use. You are not sure which of these 1,000 ones is the best one. right? And you don't have time to wait it out and see who is performing well, because again, you're in this online learning framework where we had to make predictions on each day. Okay. So what's the setup? Let's think of it this way. So there's expert 1. So there's expert 1, there's expert 2. Okay. So there are n experts. Actually, maybe let's use D experts. I think that's closer to the notation that we've been using. Okay. And for simplicity, again, I'm just going to assume that they're trying to predict a binary variable. Everything that we're doing can be generalized to real value predictions, where they want to say, okay, the stock market is going to go up by 1% or 2%. It's going to go down by 1% or 2%. All of this can be generalized there. But all we are saying now is, let's say they're just trying to predict whether the market is going to go up or down. Okay. So on day 1, we get to see the predictions. This person says up, expert 2 says down, up, down, and so on. Okay? And after all of this, we have to make our own prediction. Okay, and the same thing on day 2, we see the same thing. But after this prediction, we also get to see how each expert did. Maybe this person was right, this person was wrong, right, wrong, wrong, right, and maybe we were right. Okay? And then we get to see the same thing. Maybe this person says down, up, down, up, and so on. Okay, so this is the game that we're playing. Maybe it's like, all right, and so the game is, we see the predictions, then we make our prediction, and then we get to see the ground truth. The next day, we know whether the stock market went up or down. Okay? And this keeps going on every day. Day 1, day 2, up to maybe day n. Right? And at the end of the day, we can tally how well each expert has done. Right? How do I tally? Let's say number of mistakes. By E1, number of mistakes by E2. Let me not say mistakes, but basically each mistake is like a penalty, right? So penalty of E1, penalty of E2, so on. Our score. Okay, so this is our setup. So it's kind of like a learning problem, right? We are trying to kind of predict what's going to happen, but it's not exactly like the usual learning problem in that we don't get to see features or anything like that. We only see the predictions. In some sense, you can think of these predictions as the features, okay? But now here comes this seems like a pretty good model. But how do you evaluate your aggregation mechanism? What's a good goal to target? Any guesses? So what should be a good goal to target for you?
Your most accurate expert.
Exactly, right? Somehow if you think about it, you can't say my goal is to minimize my total penalty, right? That's just way too optimistic. Because what if all the experts that we have are absolutely bad? If you think of some website like 538, one of the things it does is aggregate polls. So you can think of each poll that it gathers as like an expert. It gives you value like, okay, Democrats are going to win the next election and Republicans are going to win the next election. So each poll is like an expert which is predicting something, and we have to aggregate those into a final prediction. Now, if all the polls that you're getting in are junk, it's not too far from reality, then we might end up with a bad prediction overall. But what we can actually hope for, what we can actually target is, our goal is do as well as the best expert. But what's the catch here? Why isn't this an easy problem? What's the catch here? Like, it seems like an easy question. I know who the best expert is. I just follow that person.
You don't know who the best expert is.
Right, exactly. With the best expert in hindsight. Meaning, I want to match the performance of the expert on day n. Who has had the best record over all these n days? Okay. So maybe the best expert was wrong for the first 100 days, right? If I threw that person out, then I'm in real trouble because I'm not going to see that person again, right? Or match that performance again. Okay, so that's our goal. I want to match the performance of the best expert. And this leads us to what is known as regret minimization. Okay, so let me introduce some notation. So let L of I comma t equals loss/penalty of expert EI on day. Okay, so the ith expert incurred this loss on that day. So loss here just means whether they are right or wrong. If they are right, the loss is 0. If they were wrong, the loss is 1. And you can have more general scenarios, like the loss could be a number between 0 and 1, right? It doesn't have to be just 0 or 1, but let's start with that to set up the problem, and then we'll generalize. So each expert incurs some loss or penalty each day. Maybe there's an expert who is absolute, who is like the Oracle of Delphi, who is never wrong, right? How do you zone in on that person? And our goal as an algorithm is to minimize what is called the regret on day n. Okay, which is you look at the total loss that we incur, and let's say L of t is our loss on day t. Okay, so that's the loss we are incurring, and we add up all of our losses. And I want to compare this to the loss of the best expert in hindsight. And how do I get the best expert in hindsight?
The one with the lowest penalty from the previous days.
Exactly, right? So one with the least penalty. The one with the least total penalty so far. Okay? So this is called regret. Like, somehow I want to minimize my feeling of regret, which is quantified here as somehow like what I should have done in hindsight. If I had perfect hindsight, I should have followed the best expert, in which case this is the loss I would have incurred. And I want to say that, okay, my performance is comparable to this. I'm not doing much worse than what the best expert does in hindsight. And our goal, as we'll see, is to design an algorithm, an aggregation scheme, which will remarkably get very small regret, even though we don't know who is the best expert. Okay? And we'll do this in an online fashion. And that will be the goal for the next couple of lectures. And we'll connect this as a, just to give a spoiler, we'll connect this to some form of gradient descent at the end of everything that we're doing. Okay? So that's all for today, but think about this goal of regret minimization. Again, it seems kind of challenging, right? You don't know who the best expert is going to be in hindsight, but we are going to get close to matching their performance. All right? Okay, so that's all for today, and we'll resume on Monday by talking about regret minimization. And another very important algorithm for doing that is the multiplicative weights update. And I'll see you all.
Not requiring the observed values to be linearly separable, right? That would just mean if they aren't, that would just mean we don't converge to zero loss.
Oh yeah, we definitely, it's working under the assumption that the observations are linearly separable and they are linearly separable with a margin.
Okay.
So it's even stronger than what you're saying, actually.
Oh, okay.
Yeah. And actually, I forgot to say, I announced it on EdStem, but I re-recorded the analysis of stochastic gradient descent and posted a new video on EdStem. So if you're here for the live class, I missed something in the proof of the analysis. So I re-recorded that portion with no audience, of course, but at least I think the proof is more understandable in the new presentation. So the last class, the beginning was a bit confusing. I recommend watching the new video. Okay.